I think we might wait like one more minute for people to show up, but otherwise we're going to start soon. Um, Divya is going to present today.
Hi everyone, we're going to be doing functions in today's meeting. So first we'll start with the definition of a function. A function establishes a relationship between two sets, namely the domain and the range, mapping every element of the domain to exactly one element in the range. So basically we have two sets, A and B. So A is a domain and B is the range. So we have some elements in A and some elements in B. So basically the function f maps elements of A to B. So we can have two elements of A mapping to the same element in B. However, we cannot have one element of A mapping to two elements of B. So we can't have something like this. This is not a function. So this is the domain of the function, and this is the range of the function. The range of the function is a set of all y such that there exists an x in the domain for which y is equal to f of x. So for example, we can look at the function f of x is equal to x squared plus 3. So we set the domain of this function as all real numbers. So basically, to find the range of this function, we can set y is equal to x squared plus 3. And now we plug in all real numbers for x. We can only get y greater than or equal to 3 because let's say we have y is equal to 2. Then we have this is x squared plus 3 for some x. We get x squared is equal to -1, which is not possible for real x. So that's why we get y is greater than or equal to -3 in the range, because we have x squared is greater than 0 for all x in real numbers. So now we have the following example. Given that the domain of f is a set of all real numbers minus a number a, determine a given that f of x is equal to 2x plus 1 over x minus 5. In addition, determine the range of f. So basically we want to find the domain of f. We have f of x equal to 2x plus 1 over x minus 5. So we can we have that when x is equal to 5, we have a 0 in the denominator. So we have x minus 5 is 0. This means that f of 5 is undefined. This means that because it's undefined, when you plug in 5 into our function, well, we get an undefined number, which means that 5 cannot be in our domain. So this means that we get that a is equal to 5. So now to determine the range of f, one way to do this is that we can rewrite this function as 2 times x minus 5 plus 11 over x minus 5. And this is equal to 2, because this cancels, plus 11 over x minus 5. So basically, we see that this part can take all real values except 0. So this part is not equal to 0, which means this can be all real numbers except 2. So basically, the range of our function is all real numbers except 2. We can see this by graphing the function. We get something like this, where this line is 2, y is equal to 2. So we get that this function never attains the value 2. So our range was the real numbers minus 2, and we get that our domain is equal to the real numbers except 5. And also to determine whether a mapping is actually a function, so given a mapping like this, we can test that it's a function by drawing vertical lines. So if all vertical lines intersect the graph at exactly 1 point, then it's a function. But if we have something like that, for example, this vertical line intersects the graph at at least 2 points, which means that this is not a function. So that's the vertical line test. So now we'll talk about function inverses. The function inverses are a function with its domain and range swapped. In other words, if f of x is equal to y, then we have that f inverse of y is equal to x. So note that sometimes the normally the negative 1 exponent means 1 over x, but that's not the case here. It just means the inverse of a function. So now we look at the following example. So we want to determine the value of f inverse of 5, where f of x is equal to 2 over x minus 3. So in the previous slide, we have that if f of x is equal to y, then f inverse of y is equal to x. So basically, we can set y is equal to 5. We get that if f inverse of 5 is equal to x, then we have that f of x is equal to 5. So to determine the value of f inverse of 5, we basically just want to find this value of x. To do that, we can solve this equation. So we have f of x, which is 2 over x minus 3, is equal to 5. And we can solve this to get 2 is equal to 5x minus 15, or 5x is equal to 17. X is equal to 17 fifths. So putting this back in here, we get f inverse of 5 equal to 17 fifths. So that's our answer. So now, instead of just determining the inverse at a single value, we want to find the whole inverse function. So given that f of x is 2 over x minus 3, I want to find f inverse of x. So to do this, so first let's set f of x is equal to y. So you have y is equal to x minus 2 over x minus 3. So to do this, we swap x and y. So we have swapping, we have x is equal to y minus 2 over y minus 3. And now we want to solve for y. So we can multiply both sides by y minus 3 to get this. So you get xy minus 3x equal to y minus 2. So then we get x y minus y plus 2 is equal to 3x. Or we get y times 1 minus x. So moving this to this side is equal to 2 minus 3x by moving this to this side. So dividing both sides by 1 minus x, we get this. Yeah, so this is our inverse. We get this is equal to f inverse of x. So in summary, to find the inverse of a function, you can swap the x and y as we did here, and then solve for y to get f inverse of x. Okay, so now we'll move on to piecewise functions. So a piecewise function is a function that is defined by several subfunctions or pieces over different intervals. So here we have an example of a piecewise function. So basically, in different ranges of the domain, we have different functions. So for n less than 0, we have n squared minus 2, and for n greater than or equal to 0, we have 2n minus 20. So the graph of this function looks something like this. So moving on to the next slide. So we have this example. So we have this piecewise function, which takes on the value n squared minus 2 for n less than 0, and 2n minus 20 for n greater than or equal to 0. So we want to find the positive difference between the two values of a that satisfy f of negative 2 plus f of 2 plus f of a is equal to 0.
Wait,
But
Divya, do you
first,
want the
to
students
simplify
to
this
solve this?
equation, we need to find the value of f of negative 2 and f of 2. So negative 2 is less than 0, which means we want to use this part of the piecewise function. So we get f of negative 2 equal to negative 2 the whole squared minus 2, which is 4 minus 2, so that's 2. Then we have f of 2. So 2 is greater than 0, which means we want to use this part of the function, 2n minus 20. So this is equal to 2 times 2 minus 20, which should be negative 16. So we have 2 minus 16 plus f of a is equal to 0, or negative 14 is equal to negative f of a. So f of a is equal to negative 14. So now we take cases. If a is less than 0, we have f of a is a squared minus 2. So we have a squared minus 2 is equal to 14, or a squared is equal to 16. This means a can be 4 or negative 4. But we started with a less than 0, which means that a cannot be 4. So one of our solutions is a is negative 4. Now for the a is greater than or equal to 0 case, f of a will be 2 times a minus 20. So you have 2a minus 20 is equal to 14, or 2a is equal to 34. Hence, a is equal to 17. And we can check that 17 is greater than or equal to 0. Hence, a is equal to 17 is also a solution. So to find the positive difference between these two values, we take 17 minus negative 4. That's 1. So that's our answer. So now, this is a checkpoint, so you guys can try it by yourself.
Does anyone have an answer?
Okay, so let's look at the solution to this problem. So first, to evaluate this whole thing, we first want to evaluate f of 4, which is the middle part. So since 4 is even, we want to use this part of the function. So we get f of 4 is equal to 4 squared minus 4 times 4 minus 1, which is 16 minus 16 minus 1, which is just negative 1. So now, to find this part, we want to find f of negative 1. Since negative 1 is odd, we use this part of the function. So we get this is equal to negative 1 squared, which is 1. Now to find this part, we find f of 1, which again 1 is odd, so this would be 1 squared. So you can see a pattern that from here on out, we're going to keep getting 1s because 1 is odd and 1 squared is just 1. So we're going to keep getting f of 1. So therefore our answer is just going to be 1. So now let's take a look at absolute value. So the absolute value of a number is defined by this function. So if the number is greater than or equal to 0, or the absolute value is simply that number. And if x is less than or equal to 0, the absolute value is the negative of that number. So for example, absolute value of 3 is just going to be 3 because 3 is greater than or equal to 0. And similarly, for any positive or non-negative number, the absolute value is going to be that same number. And then for any negative number, like negative 5, absolute value is 5 because we want to take the negative of this number. So you can think of that as just removing the sign in front of any negative number to get the absolute value. So this is what the graph of the absolute value function looks like. It's just a V-shaped curve. So let's look at the following example. So we want to find the sum of all values of x such that the absolute value of x minus 1 is 7. So in general, in absolute value problems, you want to take cases for when the value inside the absolute value is greater than or equal to 0 or less than or equal to 0. So first, let's take the case that x minus 1 is greater than 0. This means that the absolute value is just going to be x minus 1. So this is equal to 7. Yeah, x is equal to 8. And we always need to check that this value satisfies this. And it does, because 8 minus 1 is greater than 0. So x is equal to 8 is the solution. Now we want to look at the case where x minus 1 is less than or equal to 0. In this case, the absolute value is going to be the negative of this number. So negative of x minus 1 is equal to 7. So I get negative x plus 1 is equal to 7. Or negative x is equal to 6. So hence we get x is equal to negative 6. And we need to check that negative 6 minus 1 is less than or equal to 0, which is true. And so we've looked at all cases. So the sum of all values of x such that this is satisfied is just going to be 8 plus negative 6. That's 2. So that's our answer. So now you guys can try this checkpoint. Just a clarification, your answer should be in terms of p. It's not going to be like just a number. Okay, so let's go over the solution now. So if x is less than 2, then we have x minus 2 is less than 0. Hence, the absolute value of x minus 2 is going to be negative x minus 2. This is equal to p. So we have negative x plus 2 is p, or x plus p is equal to 2 if we bring the x over to this side. So to find x minus p, we can subtract negative 2p from both sides to get x minus p is equal to 2 minus 2p. So this is our answer in terms of p. Now let's look at the following example. So you want to find the area enclosed by the graph, the absolute value of x plus the absolute value of y is equal to 8. So again, we want to take cases if when each part inside the absolute values are greater than or equal to 0 or less than 0. So we can make a table. So we have greater than or equal to 0, greater than or equal to 0. So there's going to be 4 cases total. So you might notice that each of these cases represents a quadrant of the coordinate plane. So when we look at this case, we just get x plus y is equal to 8 because the absolute value of x is going to be x and the absolute value of y is going to be y since both are non-negative. So this is the first quadrant when both are greater than 0. So now we just graph this line x plus y is equal to 8. And you can do that by finding 2 points on the line, 0, 8, and 8, 0. So this is our graph in the first quadrant. Now we can look at this quadrant. So when x is greater than 0 and y is less than 0. So that's going to be the fourth quadrant. So when x is greater than or equal to 0, the absolute value of x is x. And when when y is less than 0, then the absolute value of y is less than 0. It's negative y. So you have x minus y is equal to 8. So again, to plot this line, we can just find 2 points on the line. So we have 8, 0 as a point, and 0, negative 8. So we have this line. Similarly, in this case, so we have negative x plus y is equal to 8. And this is going to be in the second quadrant because x is less than 0 and y is greater than or equal to 0. Again, we choose 2 points, 0, 8, and negative 8, 0. Finally, for the third quadrant, since both are less than 0, we have negative x minus y is equal to 8. So we choose the points negative 8, 0, and 0, negative 8, which lies on this line. So this is the shape that is formed by this graph. So we have this distance is 8, and all of these distances are 8. So we can see that this is just a square. So to find the side length of the square, we see that each side length is just 8 root 2 because this is a 45-degree angle and it's a right triangle. So since we have the side length of the square, the area is just 8 root 2 squared, which is 8 squared times 2. That's just 128. So that's the area enclosed by your graph. Now you guys can follow or try the following checkpoint. Okay, so let's go ahead and take a look at the solution. So again, we're going to take cases for when each term in the absolute value is greater than or equal to 0 or less than 0. So again, there's going to be 4 cases. So we can start off, but first let's look at the equations that each of these cases give us. So we have x plus y is greater than 0 and x minus y is less than 0. This gives us x plus y and then minus x minus y, because when x minus y is less than 0, this is going to be negative of x minus y. So this gives us 2y is equal to 20. So we get y is equal to 10 from this case. Now in the next case, when both of them are greater than 0, we get x plus y and then plus x minus y, because since both of them are greater than or equal to 0, the absolute values are just going to be themselves. So this is equal to 20. So we get 2x is equal to 20, or x is equal to 10. So in the next case, we have negative of x plus y, and then minus of x minus y. This is equal to 20. We get a minus x and a minus x, and then we get a minus y and a plus y. So this is negative 2x is equal to 20. So we get x is equal to negative 10 from this case. Finally, for this last case, we get negative of x plus y, then plus x minus y equals 20. So we get negative 2y is 20, or y is equal to negative 10. So now we need to find where each of these 4 cases lies on the coordinate plane. So to find where each of these cases lie, we need to plot x plus y is equal to 0 and x minus y is equal to 0. So x minus y is equal to 0, just y is equal to x. So that's this line. And x plus y is equal to 0 as y is equal to negative x. So that's just this line. So in the first case, we have x plus y is greater than 0. So that would be this region. And x minus y is less than 0. So that would be this region. Yeah. So we have in this region, y is equal to 10. So the line y is equal to 10 is just a horizontal line. And this is 10. Now in the second case, we have both are greater than 0. So that's going to be this region right here. And we have x is equal to 10. That's just a vertical line. And again, this is 10. And then in third case, we have both are less than 0. So that would be this region. And we have x is equal to negative 10. So that's this horizontal line. Finally, in this last region, that would just be this area. And we have y is equal to negative 10. So basically, our whole shape is this square. So we have this square, and each of these lengths is 10. Hence, each side length is 20. So the perimeter of a square is 4 times its side length. So you have the perimeter is 20 times 4, which is 80. That gives us our perimeter. Now we're going to move on to floor and ceiling functions. So we have the following functions. X. the floor of x, which is the greatest integer less than or equal to x. This is the ceiling of x, which is the smallest integer greater than or equal to x. So for example, the floor of x is basically if we take some number, basically chopping off the decimal part for non-negative numbers. And then for negative numbers, if we have like negative 4.23, we have to go. The greatest integer less than or equal to that would be negative 5. So only for non-negative numbers, you can just take off the decimal part. And then for integers, for example, the 4 of 4, that's just going to be equal to itself. Similarly, for the ceiling, so that's the smallest integer greater than or equal to x. For 4.23, that's going to be 5. And for negative 4.23, that would be negative 4. And then again, for integers, the ceiling is just going to be itself. And then we have the property that for all numbers that are not integers, we have x, the ceiling of x is equal to the floor of x plus 1. And then for integers, we have the ceiling of x is equal to the floor of x, which is just equal to x. So the graphs of these functions are shown on this slide. So this is the floor function and this is the ceiling function. So basically these empty circles and the full circles basically represent that. For example, if we want to find the value of the function at 4, we look at the dark circle, not the light circle. So at 4, the value of the function is 4, not 3. So these are called stepwise functions because they kind of look like a staircase. So we also have another function, which is the fractional or decimal part of a number. So for example, for 4.23, that's just going to be this decimal part, which is 0.23. So this is equal to x minus 4 of x. So for 4.23, that would be, we have the floor is just 4. So that's basically this part, which results in 0.23. So the fractional part of a number is always going to be strictly greater than 0 and less than 1. And the fractional part is 0 if and only if x is an integer. So we have this checkpoint. So you can try to prove these yourself. Okay, so let's look at the solution for these. So we're going to use the fact that x is equal to the floor of x plus the fractional part of x. So for this first identity, we have that we can substitute x with the floor of x plus the fractional part of x plus n. So we can combine these two since these are both integers because the floor of anything is also an integer. And since this fractional part is between 0 and 1, the floor is just gonna remove that. So we have this is equal to the floor of x plus n. So the proof of the second one is similar, but we can just try to prove these by looking at examples. So basically, since n is an integer, it kind of just disappears when you do these operations. So for example, if you set x is like 4.23, when you add an integer, it's just going to change the part before the decimal place. So the floor of x, so let's just take n is equal to 5. For the first one, we have that. So we have 9.23 is equal to the floor of x, which is 4. So we have the floor of 9.23 is equal to 4 plus 5. And this is true because this is 9. So these are easy to see just by looking at examples. And for the last one, so we have the fractional part of x plus n is equal to x, or the fractional part of x. Again, when we add an integer, you're just affecting the part before the decimal place. So that does not affect the fractional part of x. So now we have the following theorem. So we have that the fractional part of x plus the fractional part of negative x is 0 if x is an integer. So this z just means integer. And it's equal to 1 if x is not an integer. And then our second part of this theorem is that the negative of the floor of x is equal to the ceiling of negative x. So to prove this first part of the theorem, we first look at if x is integer. So if x is integer, the fractional part of x is simply 0. So hence we have 0 plus 0 is clearly 0. So if x is non-integer, we know that, so these are both positive. And we know that each is strictly less than 1. So their sum is greater than 0 and less than 2. And since it's an integer, it must be 1. So we have that x plus negative x is strictly between 2 and 0, and it's an integer. So this implies that x plus negative x equals to 1. And we get this by noting that for all real numbers, we have this. But since x is not an integer, it would be strictly less than, or strictly greater than 0. So now for the second part of this theorem, we have negative x is equal to, or the negative floor of x is equal to the ceiling of negative x. So when x is an integer, this is obvious because the floor and ceiling of an integer is just itself. So you have negative of x equal to negative x, which is clearly true. So now we can use the fact that the fractional part of x equal to 1 minus the fractional part of negative x for x non-integer, which is just this statement. So using that fact, we have that the negative of the floor of x is equal to negative of x minus the fractional part of x. This is equal to negative x plus the 4 of x, or the fractional part of x, and the fractional part of x is just this. And then we can combine this term with this term. So you have this is equal to the floor of negative x, and then we have that plus 1. This is equal to the ceiling of negative x from the property we discussed on the very first slide. So now we have this following example. So this is called Termites Identity. You want to show that for any real number a and positive integer n, we have this. So first we take the case where a is an integer. If a is an integer, then all of these are strictly, so 1 over n, 2 over n, all the way up to n minus 1 over n are strictly between 0 and 1. So when a is integer, the floor is just going to be a for all of these terms. So we have the right hand side is just a times n. And then since both n and a are integers, this is just going to be n. So this identity is true for integers. And then for non-integers, we have that floor of a is less than or equal to the floor of a plus 1 over n. So on. This is less than or equal to a plus 1. This is clear because this value is increasing because we have 1 over n, 2 over n, all the way up to 1. So now we have that this is equal to the floor of a plus 1, since 1 is an integer. So then we have that there exists an integer m, such that this is equal to a. So basically at some point, this term is going to cause this expression to spill over to a plus 1. So m over n is the greatest m such that this is still less than a plus 1. We have this is less than a plus m plus 1 over n, all the way up to a plus n. This is equal to a. So we have, so this is kind of the spillover point, and then it's going to be less than or equal to a plus m plus 1 over n, and then these are going to be equal. The rest of the terms are going to be equal. So from our definition of m, we have that a plus m over n is less than 1 because we have this is less than a plus 1, and we also have that plus m plus 1 over n is greater than 1 because this is where it spills over. So when we combine these two inequalities and solve for a, we have that the fractional part of a less than 1 minus m over n is equal to 1 minus m plus 1. Okay. So just going to use this next slide to finish the proof. So now we can see that Termites identity, the right hand side can be written as follows. And this is equal to n times the floor of a plus n minus m minus 1. And since this is the right hand side, we want to show that this is equal to the left hand side of Termites identity, which is the floor of n. And so we want to show this. So we got this inequality here, so now we're going to use this. So we had 1 minus m plus 1 less than or equal to the fractional part of a. So let's multiply both sides by n. We have n minus n plus 1 and equal to n times the fractional part of a, which is less than n minus n. Using this, we get that n times the floor of a plus n minus n, which is this quantity, less than or equal to n times the floor of a plus n times the fractional part of a. And this is equal to na because we have that a is equal to the floor of a plus the fractional part of a. This is less than n times the floor of a plus n minus n. So therefore we have that the floor of n times a is equal to n times the floor of a plus n minus 1, which is what we wanted to show here. So that finishes the proof. So now we have this checkpoint, and you guys can try it yourself now. And we'll be taking a 5-minute break now.
Okay, we'll start the Kahoot at 3:07. Okay, you guys can join the Kahoot now. I think there are 2 people still remaining. Okay, 1 person. Okay, everyone. Okay, we're going to start now. Um, okay, yeah, I think you gotta be careful because it says the inverse. It wants you to find the inverse of f. So if you just plugged in those numbers, it would have been incorrect. Yeah. Sabrina is in first place. Okay. Well, Root 29 is not an integer, so you use the floor, and root 29 is like slightly more than 5. So overall it's 5 plus 5, which should have given you 10. Jesse takes the lead. Nice. Yeah, pretty straightforward. You just plug everything in. Jesse is still in the lead. Good. Jesse, still number 1. Pretty good. For this one, I mean, you could have just looked at the answer choices, but on another way is to just try different values for the ceiling of x. So, like you could try 3, but that doesn't work. You could try 2, and then it turns out that works and gives x is 9/7. So, yeah. Hello there takes the lead. Okay, for this one, you can like expand the right side and get all of the absolute values of y together. Then it's just um, abs y equals 2, and yeah, if you got 2, -2 also works. Oh wait, okay, there might have been a problem with there might have been an error with the answer choices. Yeah, it's -4. Sorry. Okay. Yeah. Sorry about that. Okay. So for this one, you can find the largest possible one and the smallest possible one. I believe the largest possible one is um 7, and then the smallest possible one is -3. So that would give you 11 possible integers. Hello there is still in the lead. Okay. So for this one, x minus 3 and 3 minus x, they're both equal to absolute value of x minus 3. So you can combine them, and that makes it a lot easier to solve. Otherwise, you could still split it into cases. Hello there is still number 1. So you have this quadratic on the bottom, and if it equals 0, then the equation can't produce a value. So um, wait, hang on. Okay, hopefully the Discord should be gone now. And so you can factor it to find the zeros, or you can use Vietas, which is just 6 over 2 equals 3. Okay. Okay. Right. So you can factor all these to find the roots, and 64 is one, 8 and -8, and also 4. So there are 4 real numbers that are not in the domain. Oh, okay. Okay, so keep in mind that it said that the inverse, where is the inverse undefined? So that means you first have to find the inverse of f. And there's a similar example that we did in the handout. So after you do that, you can find the correct value of x. Hello there. I guess they were the only person that got it right, so good job. All right, nice job. Right, you just gotta like do it for this problem. No change in the leaderboard. Okay, for this one, you can use the table to find the values of the inverses, and you end up with 5. Okay, so 2 more problems left. Nice. Okay, hello there is really pulling away from the rest of the leaderboard. Last question. Okay. Well, the value under the square root has to be non-negative in order for it to be valid. Um, and if it's 1, it's 0, so that works. Good job, guys. Right, okay. I think Richard was hello there. Congratulations. So yeah, thank you guys for coming. If you haven't registered for the Iowa City Math Tournament, please do so. The form is on our website. Yeah, and also keep submitting your answers to the exercise leaderboard. The form is also on the Math Circle page on the website. So yeah, thank you for coming. We'll see you guys next week.